Alright, so this is going to be the last video I make before I go to bed. The final tutorial. This is for calculus and vectors, primarily focused on business students. But yeah, I'm just going to run through this really quickly. Basically, it's like, for what value of x is the function f at x equals 1 over x squared minus 1 increasing? So when it's asking, we're talking about increasing, we want to look at when the derivative of the function is greater than 0, right? Because what the derivative is concerned about is the velocity, right? It's the rate of change. So if it's increasing, that implies that the velocity is going to be positive, and we know that greater than 0 is positive. So that's specifically why we look at that. But yeah, so the way we can find the derivative is we can do two ways. The first way is the chain rule, right? So we have the derivative of f of g at x, right? So we have some function inside that is g of x and some outside. This is just going to go to f prime of the original g of x times g prime of x. So in this case, in order to use the chain rule, we're going to need to bring this piece up to here. Right, so we have f at x equals 1 over x squared minus 1. That goes to x squared minus 1 to the negative 1. Right, because negative 1 just implies that we're going to divide. So therefore, we have f prime of x equals to this. So I wrote out the steps over here. Right. So what's inside? We have x squared minus 1. What's the derivative of that for g prime of x? That's 2x. What's the power on the top? Right, so we're going to use the power rule here. So say we have like x to the 2. Well, that implies that we're going to take the power down, have our original, and then have 2 minus 1. Right, so we see we did that. Negative 1 minus 1. Take the power down. That's negative 1 goes to negative 1. So we have what the derivative is. Right, the second way to do it, which is probably the better way here, or in general, is the quotient rule. That's basically like, suppose we have some function on the top and bottom. This is going to go to the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Right? In this case, it's better to use that because we have a constant on the top. We know that a constant, the derivative of a constant, this is just going to go to 0. So that's going to get rid of this piece, which is going to make it much easier. We won't have to deal with factoring or simplifying. So yeah, we just get this function. Now the next part we want to move on to is when it's increasing, as I said. So f prime of x is greater than 0. We have our f prime of x. So we can build this little table here to check for positive or negative signs, right? Because if it's positive, it's increasing. Negative, it's decreasing. So we do this. I set up this little table because we're going to notice that x squared minus 1 squared is just going to be greater than or equal to 0 for all x element of r. I didn't give a super complex proof. I just gave a basic example. The proof isn't really relevant for this course, but yeah, I think I've done it before, but it's like let a greater than 0, a element r. Then we have the first case where we have negative a inside squared. That's just going to go to, well, a. Negative a, negative a, a. A squared is just going to go a, which is a. Right? We're going to end up with square, square. And then 0. Well, this is going to be, well, 0 times 0, 0. Right? So in any case, we see that this is always going to be positive or 0. So we can say that for all x element of r, it's going to be greater than or equal to 0. Right, so we know that, so we can just put positive, positive. And we don't need to consider if it switches or flips, right? So yeah, usually whenever you set up a table, I think we're going to do it later as well, you just put the roots there, right? Because those are potential points where it could flip. But yeah, in any case, setting up the table with our different roots, our factors, we see that we have positive between negative infinity 0 and negative between 0 and infinity. That means it's increasing between negative infinity and 0, decreasing between 0 and infinity. Right? However, the last thing we need to consider is the restrictions or the domain, right? We have 1 over x squared minus 1. Well, that's going to imply that we have x squared minus 1 does not equal 0. Solving for this, we see that x does not equal plus or minus 1. Originally, we would have just said that it's increasing between these two, but we have to then state that it cannot equal negative 1, right? So it cannot be increasing here. It cannot equal that. So when we set up our interval of increasing, we're just going to put a little disjoint thing here. We're going to connect these by union. Negative 1, less than negative 1, greater than negative 1. And we have our interval. Yeah, that's it for that. So find the critical points of f at x equals x cubed minus 3x plus 2. So when it's talking about the critical points, it's just asking like, when is the derivative equal to 0 or it's undefined, the function. We don't have to worry about undefined. That would be the case, as I said earlier, of like x squared minus 1, right? X cannot equal 1, negative 1. Yeah, so this is not something we have to worry about here. So here, if we want the critical points, well, we want the derivative, so we're going to take the derivative of this. How we do that is, once again, we're going to use the power rule, and I can just give an example. Suppose we have like 3x squared, like this. Well, what is this going to go to? Well, we're going to bring the 2 down. We're going to have our original. And then this, very important that you do this, it's just 2 minus 1. Right? So that's what it's going to be, and if you just wanted me to show that, it's going to be like that. Okay, so we're going to distribute our derivative throughout the entire expression. Like this, this. Evaluate using the power rule, and we're going to end up with this. Here, we can factor out a 3 to make it simpler to solve. So then we get f prime of x equals 0. That's going to imply that we have 3 bracket x squared minus 1 equals 0, which is just x squared minus 1 equals 0, which implies x is equal to plus or minus 1. The last thing we wanted to find is the points. Right? Since we wanted to find the points of our respective roots for our derivative, that means we're going to want to find the y values, right? So this y1 is going to be f at x of 1. And y2 is going to be f at x of 2. Right, so y1 is equal to f of 1. Sub that in to find the point. We find that 0. y2 is going to be equal to f of negative 1. Sub that in to find the point. So therefore, the critical points are at 1, 0 and negative 1, 4. Right. Okay, so this one's a bit long. Find all the critical numbers, all the intervals of increase and decrease, all the local minimum points, and all the local maximum points. So once again, if we're wanting to find the max or min, we're going to want to look at the derivative equal to 0, right? Because what this implies is we have 0 velocity, which, in conjunction with continuity, would imply that this is a turning point. If we have a sign change, if we have positive, negative, or negative to positive, right? It could be an inflection point. We could have positive, positive, and like a 0 in between. Like an example of that is like this, right? Right here. But yeah, so that's it for that. This is the basic idea. So as I said, we want to find the derivative at 0. So find the derivative of a. This is just going to be the power rule once again. We're going to get this. We notice we can factor out a 15 and an x squared to get these pieces. We can factor further to get x minus 1 and x plus 1, right? Different squares. So once we find these values, now we're going to want to set up a more complex table, right? Because these things could impact each other. We still have an x squared though, so this is always going to be positive. But our x plus 1 and x minus 1, those are going to change, right? So we're going to want to set up the table like this. This time I included all the roots. You don't have to include 0 because that's not impactful here, but I just did that this here. So, and you would state the bounds of the domain to whatever is set in the question. Here it doesn't say anything, so you can just assume it's negative infinity, infinity. But yeah, so we're going to check the values between for each factor. Negative infinity and negative 1. What's that going to be for x plus 1? Well, it's negative. What about after negative 1? Well, it's smaller than 1. Right? Negative 1. So that means it's going to be positive. And something we notice is anytime a individual factor switches signs, if it goes from like negative to positive, it's going to be always positive after that, right? So you can use that to fill out the table more quickly, if you notice that. But yeah, so this is always positive. Then we look at x minus 1. Well, that's only going to be positive after 1. So now we notice that between here it's positive, between here it's negative, negative, positive, right? So what exactly is this going to give us? What's going to give us that it's increasing between these 2 points, right? Like here and here, here and here. I'm just going to change that. Negative infinity, negative 1, decreasing, negative 1, 0. I think I wasn't looking right. There you go. Okay. Yeah, so this is the intervals increasing, decreasing. Originally, I didn't look at the table right, but there you go. Okay, so what is this going to imply? Well, this is going to imply that we have a local min at x equals 1. Why is that the case? Well, we're going from decreasing to increasing, so, well, it's going to look like this. This also implies that we're going to have a local max at x equals -1, because if we look up here, well, we're going to notice it's increasing to decreasing, so it's going to create a maximum. Right, these are little visual elements that you can consider drawing yourself to make it easier to look at. But yeah, so what's the next thing? The points. Oh yeah, so we found the x values of our max and min. So now we're going to want to find the points themselves, which is just our y values. So we can sub in our x values into the function, 1 and -1. That's going to give us -2 and 2 respectively. So therefore the local min is at 1, -2, and the local max is at -1 and 2. Okay, so the next one's pretty much just the exact same. F prime of x is equal to 0, right? Here we notice it's a rational function. We could bring it up to use the product rule and then the chain rule, but that's a mess. So, right, quotient rule is really fast. After doing the quotient rule, right, which is just f prime of x, g of x minus f at x, g prime of x over g of x squared. We get the derivative. This is very similar to the question in 1. Right, we're going to set up a little table. Once again, this is squared, so this is always going to be positive. This is just going to be 0, right? -8x equals 0, just goes to 0. And therefore, from this going from positive to negative, right, we're going to notice that this is going to be a maximum. Right? Increasing, decreasing, max. If we want to find the point, we just do y1 is equal to f at that point, which is 0. And that goes to 0, so therefore the local max is at 0, 0. Okay. Once again, though, we have a rational function, so we're going to want to consider the roots in the bottom. 1 over x squared minus 4, that implies x squared minus 4 does not equal 0, which implies x does not equal plus or minus 2. Right. So if we want to include the intervals of increasing and decreasing, we're going to want to consider that. We have -2 here, too. So it's increasing between here, so we're going to disjoint it here. -2 and R2. Right, so less than 2, greater than 2, less than 2, greater than 2, -2, -2. But yes, that is it for that. Yeah, good, okay. Just make sure I looked at this table right, because, yeah, okay, negative, yeah, yep, yep. Okay, good. Everything is good. I do not want to leave wrong answers for you guys. Oh, this one's a mess. Compute the price elasticity of demand of a product whose demand function is P equals 15 times 0.99999999. What do I oh wow. To the X at the current production level of 850,000 units. Is the demand elastic or inelastic? Should we change the price of the product? Right. These numbers are ridiculous, but anyways, whenever we were talking about elasticity with respect to some unit, right, we're going to want to consider that that's equal to P of x over P prime of x. So we're going to use that here. We noticed that we needed P prime of x. We do not have it, so we're going to need to find it. To do that, we can just, well, take the derivative, take out the 15 because it's a constant coefficient. And then we can use our little rule here such that we have ln of the inside and then just a to the x, right? That's a little derivative rule. After we did that, we found our P prime of x, right? As I said earlier, the elasticity was determined by P of x over P prime of x. Well, we have 850,000 units, which is our x. So therefore, we have P of 850,000 over 850,000, P prime of 850,000, which is a ridiculous number. So we're going to approximate that. It's approximately equal to negative 1.17647. Okay. So now we can determine if it's elastic or inelastic. And we notice that the demand is elastic, as we have the magnitude of the elasticity calculated is greater than 1. From that, we can determine that raising prices decreases our revenue, so we should decrease the price, right? the last one. Shaki makes and sells backpack danglies. It's such a funny word. Danglies. Oh, no, a little dangly here. Right, the total cost in dollars for Shaki to make Q danglies is given by CQ equals 75 plus 2Q plus 0.015 Q squared. Find the quantity that minimizes Shaki's average cost for making danglies. Once again, we see minimum. So what does that tell us? We're going to want a derivative here equal to 0, and we're going to make sure that it's actually a minimum. Like check, min. Sometimes it's a max. Sometimes it's an inflection point. Okay. What is it? Oh yeah, since it's asking for an average cost, I actually got a few questions about like how do we know that this is the average function, or how could we find that? So I'll give a little example. So imagine we have 20 of something. We put it into a machine, it gives us 60 back. Right. So if we're talking about like an average, we can just think about it like, how much output did we get per input? Well, to determine that, we can just take our output and divide it by our input. That tells us that we get, in this case, 3 output per 1 input, which gives us our average, right? Because if we multiply that thing by our original input, that's going to give us back to 60, right? Average times the input equals the output. So similar concept here. We have, in this case, our function input is just going to be imagined as x, goes into the machine. Our output's going to be 75 plus 2x plus 0.015x squared. That's going to be our function. So if we imagine it like this, well, this is what it is. We can just take our output over input. Input is just x. Output is just function. So we end up with the function over x is our average, right? So that's why that's the case. Since it wants us to minimize with respect to the average cost, well, we're going to take the average function, and then we're going to want to find the derivative. So to minimize, we can look at C average prime Q equals, that's a nice mix, equals 0. So C average prime Q, we can just use the quotient rule because it's a rational function. After doing that, we arrive to this. As I mentioned above, we want to find the minimum. Right, so we're going to set that function equal to 0. We notice that the bottom is just going to go, fade into the void, right? Because we have 1 over Q equals 0. Well, say goodbye. Right, just multiply that over. Yeah, so we just have the top left. To solve that, we're going to take this over here. Then we're going to divide this. And then we're going to take the square root of this, right? That's going to give us Q equals plus or minus 50 square root 2. Notice that in this context, the negative solution is not valid, right? We cannot make negative danglies. Little janglies, little tingly danglies, right? So you have to take the positive one. Once again, make sure to check that it's actually a minimum. Sometimes it'll be a maximum. If you take the maximum, well, you did the opposite of what you wanted to do. Yeah, so the min average cost then will be our positive solution because we checked that it is. Therefore, which is just going to be Q equals 50 square root 2, which is like 70 something. But yeah. I think that is all. Yeah, it was good.